Okay, students, welcome back. So let's wait for 1 or 2 more minutes so rest all will join. Then we'll continue. Okay, so now we can continue. So now we're talking about the cloning vectors. So when we're talking about cloning vectors, now what are their characteristics? So the first characteristics is it must be in small size. So now why we need their size should be small? So as we are talking about that they should carry a large amount, a large load. So when they should carry a large load, then their themselves load should be less. So when they're nowadays you might be hearing that whatever the vehicles they are coming a lightweight. So when they are coming lightweight, it means their average is going to be better and they can carry a large load also because their self load is less. Because when their self load is high, their self weight is large, so then they have to carry themselves also. Similar type of thing is there in case of your cloning vector also. If their size is big, then the amount they can carry is going to be small. So for example, if your plasmid vector size is more than 10 kilo base pair, then the transformation efficiency is going to be very low. Simple means you can't transform, which you can't transfer it to a cell. So when you cannot transfer this to a cell, then it means it is of no use. So this 10 kilo base pair is a total load. Means your plasmid vector plus your gene of interest or insert of interest. So if your plasmid size is going to be 9 kilo base pair, so 10 minus 9 is going to be 1. So it means your vector can carry only 1 kilo base pair in size. That is very small load. So what you can do, if you decrease the size of your vector, if your vector size becomes like 2 kilo base pair, now this vector can carry 8 kilo base pair of your DNA load. So this is the first characteristic of a vector. It should look, its cell size should be small so that it can carry a large DNA. Okay. So the second property is it must be self-replicating inside the host. So when you transfer this vector after loading it with your gene of interest to a host cell, now host cell, this DNA is going to be serve as a foreign DNA. Then it may degrade it also. So for what property should have, it must be self-replicating. So if it is self-replicating, then it can be, its degradation can be avoided. Okay, and it is self-replicating, its number keep on increasing. So after every cycle, a new cell is going to be formed, a new vector is going to be formed. So this is the second characteristic. It must be self-replicating inside the host. So now the third property, it must possess a restriction site. So now you may ask that, but for what you need restriction sites? So restriction site means restriction endonuclease site. So this is the location on your vector, your DNA vector, where your restriction endonuclease can produce a cut. So when restriction endonuclease is going to produce a cut, it simply means it is going to break it down. And now, after breaking a cut, putting a cut, you can join a new DNA. So as we were referring about the metro, means your daily metro is going to carry a large number of seats. So as it must have a large number of cloning sites, and these cloning sites are also called the restriction sites. So more number of the restriction sites are there, more locations are there where you can produce a cut and insert your DNA. So now, as you may know that we have talked about three types of enzyme. First is the restriction endonuclease. Job of it is producing a cut. Second thing is your uh, ligases. Job ligases to join. So after producing a restriction cut, you can put your interest, your segment of interest, and add the ligase. So ligase is going to reseal it. So by this way, you can upload, you can add your DNA which you want to be carried by your vector. Okay. So the fourth property is the introduction of donor fragment must not interfere with the replication of the vector. Okay. So what we are doing, we are now, our main job is it should carry the DNA. So when if we are inserting our DNA into this vector, and after the inserting, we found that now the self-replicating property is going to be harmed. Means the restriction site that we are talking about, it should not be there in the self-replicating site. So self-replicating site in your vector is going to be, we also call it as the origin of replication. You all know that origin of replication is a location from where your DNA replication starts. So this origin of replication must be present in your vector. Okay. So next property is it must possesses some marker genes. As I mentioned that your glasses must be clear so that from outside I can see. Okay, so here in our case it is DNA, we can't see by eyes, so we need some markers so with that we can see it whether your gene of interest is uploaded or not. So these markers are called marker genes. So these genes are going to be some characteristics that are going to come after inserting your vector inside your host. So it must possess marker genes such that it can be used for later identification of the dominant cell. So this property we want to check whether the insert that we are going to the vector that we are transferring is carrying your gene or not. Next is must possess multiple cloning site. So multiple cloning site is from same as we mentioned in the third restriction site or restriction nucleation enzyme. The purpose of both are same. Restriction sites and cloning sites are same thing. Your vector must possess multiple cloning sites depending upon your requirement at which seat you want to put your DNA, you want to make your DNA to fit, you can add. Okay, so now I'm giving you some example of your vector. So how you can generate it, how you can design it. So as when you are talking about these properties, so first property that small size. So like when you isolate your vector from your cell, the normal plasmid that you are getting, the size of normal plasmid is going to be around 200 kilobase pair. So the restriction, the plasmid enzyme that you are getting that are present in natural cells, their size is around 50 to 200 kilobase pair. So very smaller is around 200, simply I mentioned 50. There is a very large size. As I mentioned, if size is going to be 10 kilobase pair, then the transformation efficiency is going to be low. So we can't go with the so large plasmids. And then when you are designing your plasmid, so what you have to do? You have to cut down, you have to shorten your plasmid so that it came within the frame of your requirement. Okay, so here the example that is the PBR322 is a plasmid. It is the first plasmid design, and as the name is there, PBR322. The PBR is with the name of the discoverer. So, so this is your assignment. So you have to come up with the name. P stands for the plasmid, and 322 is their number. Okay. So what it have, what are the characteristic size is 4361. This is the size. What it have, it is isolated from E. coli. It is present in E. coli, so you can transform back into E. coli also. So both the type of E. coli are there, which can have already having the plasmid or which are devoid of the plasmid also. Cloning limit. So cloning limit is 0.1 to 10 kilobase pair. So at the maximum, you can go with the 10 kilobase pair in it. So because after adding 10, size is going to become 14.361. Then to be it is going to further decrease the efficiency of transformation size will be higher than 10. But we can go at the max 10 in this case. Marker genes. So you are also having a marker gene in it. Marker is the ampicillin and the tetracycline. So these two are the antibiotics. So if your genes are present on your plasmid and you transfer this plasmid, then that cell is going to sustain, that's going to survive in the presence of these two antibiotics, ampicillin or tetracycline. Then coming to the restriction site, so restriction site is there, as you can see, EcoR1, HINT3, SAL1, PST1, and OLE1. So these are the restriction sites. And the one, as I mentioned, it must have the cell replication properties. It have the OREC site. The pole E1 origin of replication is going to have. This is the origin of replication it have. So from this E. coli, that the polycene, the plasmid is there. So that plasmid, from there you take out the origin of replication from the plasmid which have the ampicillin resistant gene. You take out the ampicillin resistant gene and then you combine it. And from another one you have the tetracycline resistance. You can that you combine, and in that also you inserted this restriction site EcoR1, HIL3, PST1, SAL1, and so on. So if you cut your gene with a SAL1, then what is going to happen? Then this gene tetracycline TRT is from the tetracycline resistance. These tetracycline resistant gene is going to be broken down, and you inserted your gene of interest here. Means by breaking at the SAL1 site and inserting your gene, your DNA of your interest, which is going to disturb your tetracycline. So now this disturbed tetracycline, if you insert within a cell, then the cell is going to be resistant to ampicillin, but it is going to be sensitive to the tetracycline. Wherever those cells which are having this empty vector is a known ligated vector that is going to be resistant to both ampicillin and the tetracycline. So this is the one thing how this plasmid vector is going to work. Next type we are talking about the viral vectors. So in the viral vector that we know that the lambda phases are there, bacteriophage that we call them. So lambda is a bacteriophage. So these are the phages, these are the viruses which infect the viruses. So here the size is going to be a bit larger. So you can see the 48.502 base pair is the size of it. Here we don't have a constraint of that 10 kb type in the insertion, but as you can see, load you can combine only 4 to 5 kg base pair, so only a small load you can give to it. So, but here are aiming to give a large load, so we need better properties so that you can insert it, so you can short it down so that you can carry a larger amount. Okay, so when you talk about the origin of replication, you don't need origin of replication here. These phases are having its own origin of replication. That is the OAT is there. This is the origin of replication for this viruses. So there is not bacterial origin; it is viral in origin. When you are seeing the restriction sites are there, so the restriction sites are there again. You can insert your restriction site of importance and replication genes, lysis genes, and the code genes. These genes they require assembly. So in the biology class, how the virus are going to replicate. So when virus replicate, and when the lysis what occur, virus will come out. There must be capsid around it. So the capsid is also called the port proteins. So they must for these things must be inside that not only they are going to be self-stable, otherwise they won't invade to the next step. Another one is the plasmid. So plasmid I mentioned it has to do the property of your virus and bacteria. Sorry, bacterial plasmid. So that we call the plasmid. So as you can see, these are post sites are there. These post sites help in their packaging inside the virus, and these you see origin of application is the help in the application inside the bacteria. And ampicillin is a resistant marker, neomycin is also a resistance marker, and BAMH1 is a cloning site. Okay, so these are the property of the plasmid. So the example is the superphos one. Size is 7.9 kilobase pair, and it has combined features both class and the plasmid, as I mentioned you. And the cloning limit it can carry a large amount, so the plasmid can carry up to 10 kilobase pair. It can carry up to 30 to 15 kilobase pair. So further, when we are moving to different types of property, so now how to design it, depending on the property that you need. And I mentioned one, so that our virus application formula, you need a core site. So these core sites, if they are between any DNA that present between these two core sites, will be packaged. Okay, so this is the property that it must have. Then it must have all the port protein information and protein required here also. Then artificial chromosomes. The chromosomes, as mentioned, two types of chromosomes. One in the eukaryotes, we are having human chromosomes, and in case of bacterial, also the bacterial artificial chromosomes. And if you're using human chromosome, we call it a human artificial chromosome. So depending upon your requirement, you can all the properties as the PUD, PBS is a bacterial artificial chromosome. This X shape is a human artificial chromosome. And East also another chromosome, you can also make the East artificial chromosome depending on what organism of your target, in which organism you want to transfer your gene. You can design artificial chromosome also, you want to clone your gene in bacteria. You can have bacterial artificial chromosome in yeast, you can have yeast artificial chromosome. For human cells, you can transform, and you can have the human artificial chromosome. Okay, so these are the few things. Just a quick, I give you the glimpse of the vector and the construction of vector. So how to construct a vector? So if I give you an assignment, then if I ask you that I need a vector in which if the PBR322 is there, this is not having uh, BAM-H1 site. So how we are going to insert a BAM-H1 site? We need a BAM-H1 site. Or if I give you one thing, I further want to decrease the size of figure 322. What I can do from it? Yes. What I can remove? Yes, friends.
Sir, can you repeat what you just said?
So two questions I give you. One thing, it do not have BAM-H1 restriction site. First thing, I want that to insert into it. Second thing, size, as I mentioned, size is 4 kilobase per hour. So if I want to bring it to smaller size, so I can load some extra DNA over it. So what I can do with this one? Give a thought over it, and I'm giving you 10 minutes. So after 10 minutes, I will ask you again. So give it all think about it. So two things you have to do. One, inserting a restriction site. Second thing, decreasing the size of it. So what you can remove it from it, which is not as much necessary that you think. Okay, so this is 3:36. So I'm giving you 10 minutes. So I will. So I'm giving 14 minutes for say. So I will come back to you at 3:50. So then we'll discuss what you are giving. I will take your answer, and I will also give you the answer. Okay, students, so welcome back. So, what are your thought on it? So, who will answer?
Sir.
Yes.
So, in case of the BAMH1 site, isn't it already present on the PBR 322? I mean, the tetracycline resistance site is BAMH1, right? So, are you saying besides that we'll have to add a new one?
Sal one.
No, so
Sal
but
one
the
acid.
tetracycline resistant site also will usually, I'm saying in general, the properties of PBR
No,
322 won't.
Mansini, question is
Huh.
focus on what image you are seeing.
Oh, okay.
Okay. Question is
Okay.
based on the what
Okay.
image you are seeing. It's on this image. What real vector map is going to have, that is a different issue. But my question is focused on what this image is showing to you. Okay, so on this basis, just answer.
Sir, so based on that, then we like it says that it has a restriction site for various restriction endonucleases. So, using one of those, we would have to cut a piece of cut out a piece in a appropriate position and then insert the gene, and then after that ligase it again so that it can be
Yes, this is
recombined.
a right answer, Manaswini. So we can do one thing, that any restriction site is there, we can utilize that, break a cut, put a cut using that enzyme, and insert a segment which contain restriction site of your interest. Like dimension we are referring, so whatever the site of dimension is recognizing, we can insert that sequence in between so that it can have that restriction site also. This is the right answer. And next question is, I want to decrease the size. So what can we do?
Sir, I'm not sure, but can we divide it into two?
Hmm?
Can we divide
Divide
this
into two
base pair
means
into
what?
two?
How?
I mean, in two fragments.
Yeah, we have to divide. So what you will do to divide it?
Uh, sir, I mean to say the half of it we can divide and make a two fragments, and we can insert in the two sides.
Is what to? Uh, that's my question is that what to remove? Divide means what to divide? How to divide? You need all the properties that I mentioned in this one. So you need size small, you need self-replicating property, you need, so it means you can't remove the origin of replication. You can remove the restriction site you need. You need markers also. One marker you can't remove the ampacillin, etc. So
Sir,
simple thing as we mentioned
I
that
think
answer is that you are having two markers here, ampacillin resistance and the tetracycline resistance. So if your job is done, if one resistance marker can serve your job, in that case you can remove the other one. So you can remove this ampacillin resistance per se. Then and remove this ampacillin and join back. So in that case, so your tetracycline marker is going to serve your job, and your size will also be reduced. So any a part of your vector that you feel that it's not necessary for your job, so you can remove that. Okay. So this is a bit answer to you, these two questions that you mentioned. And now I'm sharing you two videos. So please listen and watch the videos, and they will give you some more explanation. I hope it is visible to you. Hope it is visible
Yes,
and
sir.
audible both. Is visible and audible both?
Yes, sir.
Are you asking anything? Is anyone asking something?
No, sir.
No, sir.
Okay, so these slides tell you the most of the how these vectors are important, and depending upon your host where you want to transfer your gene, you have to change your vector. So as a single vehicle can't do all the jobs, here also a single vector can't do all the jobs. So depending upon our requirement, we keep on changing our vector. What property we need into the vector, we keep on inserting it and keep on removing it. For the insertion and the removal, the enzymes that we're talking about, the manipulation enzyme, DNA manipulation enzyme, your lipases, your restriction endonucleases, and other modification enzymes that we all take care and perform our required things. Okay, so now I'm sharing you the second video that is going to show you some animation. So that animation will describe you how really things are working. Okay, hope it is also visible to you. Okay, students, so these are the some features of your vector. So if you want to design of your interest, and most of these vectors that you need for your experiment, they are available commercially. And if your experiment needs some special things, then you can design your vector also as of your choice, as of your need. But most of our need being resolved by whatever the commercially available, so we don't need to synthesize it or we don't need to construct it. But for the purpose of just your knowledge, it is you must know how to construct it and how to get it. So in your theory part also, when we are going to talk about these plasmids and these vectors, so how this first vector being discovered, we will also talk about that. So meanwhile, I'm resting today's discussion now. And now please turn on your camera when I call your name, and so I can mark your attendance also. Just a moment. Okay, Demetrius. Demetrius.
Present, sir.
Tridev. Keep on turning on your camera also, Demetrius and Tridev. Manaswini.
Present, sir.
Adesh.
Present, sir.
Present, sir.
कौन प्रेजेंट हुआ भाई? आदिश हुआ, कौन हुआ?
Sir, Tridev, present.
Okay, Adish and Tridev.
Yes, sir.
Yuvraj.
Excuse
Present,
me.
sir.
Sanjana.
Present, sir.
Nehal.
Present, sir.
Atoiba. Atoiba. Atoiba is absent. Devanshi.
Present, sir.
Nandini. Nandini.
Present, sir.
Kshitij. Kshitij. Janvi. Janvi. Shivani.
Present, sir.
Shakti.
Present, sir.
Rupal.
Present, sir.
Sahiba.
Present, sir.
Shita.
Present, sir.
Amrita. Namrita. Tanvi. Tanvi.
Present, sir.
Yukta.
Present, sir.
Ayushi.
Present, sir.
Vivek. Vivek.
Sir, he had a bad network, he said.
Okay, so students, those who are absent, I'm calling their name. So Atoiba, Kshitij, and Namrita. Atoiba, Kshitij, Namrita.
Sir, I already set my present attendance.
हाँ कर देंगे ना, आवाज नहीं आई थी. Okay, Atoiba and Kshitij, these two are absent. Rest all are present.
सर मैं भी प्रेजेंट हूँ. सर वो नेटवर्क
आते बीच में. Okay, so Atoiba is absent. Rest all are present. Okay, so thank you all. Stay safe. Stay happy. Good day.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.